Hey guys, we are starting a new unit today. We're going to be looking at three-dimensional vectors. Yay! So here's a picture, just kind of give you a little idea of what a three-dimensional vector would look like. So let's jump to our lesson. So the first lesson, we're going to look at vectors in space. So let's take a look at this. So we have a Cartesian, a three-dimensional Cartesian coordinate system. So if you look right over here, this is a indication of the three-dimensional Cartesian coordinate system. Let's remind ourselves about the two-dimensional one. So 2 dimensions, I just have x and y. So we just have 4 quadrants in 2 dimensions. In 3 dimensions, I hope that you can see, we basically have 8 quadrants. We have this 4 sections on the top of this little grid and 4 sections underneath. So there are octants. In 3 dimension, we have octants. All right, so let's look at some vocabulary. A displacement vector. We didn't really use that when we were talking about two-dimensional vectors, but it really is the same concept. A displacement vector is a vector that is the difference between the initial and the final. Basically, it's a vector in standard form. So here is our displacement vector. We would just simply do, just like we do in 2 dimensions, we would do the end vector minus the beginning and so forth, end minus beginning. In 3 dimensions, we add vectors just like we do in 2 dimensions. We would simply add the horizontal components, the vertical components, and then the 3-dimensional components. The z component. Subtracting, same kind of thing in 2 dimensions as in 3 dimensions as in 2 dimensions, and scalar multiplication. We have some constant 2 or something. We would distribute it just like we do in 2 dimensions. So that really is no change there. Going into component form, let's look. There's no difference. So this is component form for AB. If A is the x1, y1, z1, and B is the x2, y2, z2, we find the component form of the vector AB the exact same way. We would do end minus beginning. So you would see the x of 2, which is my end x value, minus the beginning. So here's my horizontal component, vertical, and then this would be our z component, our 3-dimensional component. To find the magnitude of the vector, same formula, we're just adding a dimension. Still is the square root of, the x component subtracted and then squared, plus the y component subtracted then squared, plus the z component subtracted then squared. Same kind of thing. And that's this basically. This is if we were right here with the vector AB. Typically, we would have already done this, and we would just have single numbers here. We would have already subtracted. This little diagram is showing us going straight from this, creating the components of vector AB into looking at its magnitude. But basically, it's just like before. So here, this is what they've created. They're calling these components A1, A2, and A3. We would simply square A1 and A2 and A3 and then add them together. So nothing is different about that. Finding a unit vector. So it's called normalizing. If you remember that from the last unit, when we normalized a vector, we turned it into a unit vector, not the unit vector I, j, or k, just a vector with a magnitude of 1. And it is the same formula. You would take your vector in component form and you would divide it by the magnitude of that vector. Same thing. And it's called a unit vector u in the direction of vector AB. Just the way that it's basically, the concept is we have taken the vector, that's AB vector, and we have shrunk it into one unit, basically one length long, but it's still in the same direction that the original vector was in. That's what those words mean, a unit vector u in the direction of AB. Same formula. So this is just kind of a diagram. We're going to draw a vector in just a moment. It's just an idea going from point A to point B. The distance formula, distance between 2 points, we have points in 3 space. And so the distance formula is, you know, amazingly just the same as in 2 dimensions. We're just adding a third dimension. So if I want to find the distance between 2 points, point A and point B, I would simply use this distance formula. And we can find midpoints in space, in 3 space. Again, it's pretty cool. We're just adding a dimension to each of these formulas. We aren't really changing the formulas. We're just adding a third dimension. So our midpoint formula would just simply require us to find, add the 2 x values together, divide by 2, add the 2 y values, divide by 2, 2z, divide by 2. So pretty much nothing terribly new. It's just that we're adding a dimension to all of these things that we've been working on for quite some time. So that's a little bit of an overview on 3-dimensional vectors. Let's get to the examples on the next slide. Okay, so let's look at our first example. We are asked to draw a sketch of the position vector 3i plus 5j plus 7k. So you recall I and j, a vector written in terms of I and j. Now, yes, we get to write a vector in terms of I, j, and k. Isn't that super fun? Or we can put it in component form if we wanted to. 3, 5, 7 would be our component form. That's just the 2 different forms that we have in terms of I and j or component form. So they want us to sketch it, so let's do that. We're going to sketch it by building a box. In 3 dimensions, it's a little bit of a challenge to draw it for some of us, not for others, but for some of us it's a challenge to draw in 3 dimensions. So we're going to basically build it from a box. Our coordinate system, there are 2 ways to do the 3-dimensional Cartesian coordinate system. What we do is we choose, this is our x, that's our x-axis, this is our y-axis, and this is our z-axis. Since there are other ways to write those, it is important that you label those. The other way to write it would be to reverse this x and y. That would be the left-handed type. We do the right-handed type where x is here and y is there. So x comes out towards you and y goes away this way, kind of, you know, like the 2-dimensional x-axis goes, so that's what we are looking at. So what we're going to do is we're going to go along each axis and we're going to plot. I'm just going to put a little dot where they are. So x of 3, this is the positive direction of x of 3, so we would just go 1, 2, 3. I'm just going to put a little dot here to just kind of remind myself where I am. The y value is 5, so I would go along here 1, 2, 3, 4, 5. I just put a little dot here to kind of think about where I am. And the z value is 7, so we'd go 1, 2, 3, 4, 5, 6, 7, and just put a little dot. What we're going to do is we're going to create basically a prism, a rectangular prism is what we're going to create out of those dots. So I'm going to start with the x one, and I'm going to follow this across to the y. So we're going to meet those like this. We'll meet x and y right there. So there's the bottom of my little box. And I'm going to take this and I'm going to come up and meet the z one up here. So there's the height of my box. We'll go ahead and follow it along like this. And what I'm going to do up here is mirror this. I want this to be parallel. So this is going to come up like this, and this needs to be parallel to this side. So I'm going to try best I can to make this parallel, and then I'm just going to follow that down. So then I do likewise over here. I want to make this little guy parallel, and I want to follow this up, and then this would come over. So there's my box. My point, basically 3, 5, 7, is right here. Now let's just change the color of it, just for fun. All right, so that's my point right there. And my vector would go from the origin to this point. There's my vector. So they're asking us to, that's point P, so let's label that as point P. And they want us to write the coordinates of that point. So the coordinates of that point would be 3, 5, 7. Now they want us to find the length of that vector, vector p. So we would just do our brand new formula, right? But in 3 dimensions. The magnitude of vector p is going to be the square root of 3 squared plus 5 squared plus 7 squared. That's how we would find our magnitude. And that's going to give us the square root of 83. So that's the length of our vector p. The reason that we do this little rectangular box is, to be honest, it just kind of helps us to envision that that is in 3 space. Where I know we're drawing on a 2-dimensional object, but that really kind of helps us to get a feel for what that vector would look like in 3-dimensional space. So there is our first example. Hopefully everything is okay with that. So let's look at our second example. So now we want to find the displacement vector from point A to point B. And they've given us the coordinates of those points. And use the result to find the distance between the 2 points. So basically they're just asking us to take these 2 points and write a vector. That's all they're asking us to do. So the displacement vector, vector AB, would be, we would do end minus beginning. 3 minus 8 would give us a negative 5. And then 10 minus 2 would give us an 8. And 4 minus 13 would give us a negative 9. So that's what they're asking us to do. That's what a displacement vector from point A to point B looks like. Now we want to use that result to find the distance between the 2 points. So basically the distance between the 2 points is simply the magnitude of that vector, right? That's all it is. So we would just do our distance is basically the magnitude of that vector. So that would be 25 plus 64 plus 81. And so that would give us the square root of 170. That would be the distance between point A and B. So this is simply the magnitude of that vector. That's all that is. All right, so part B says find the position vector to the point 70% of the way from A to point A to point B. Write the coordinates of the point. This should sound very familiar to us. We did this in 2 dimensions, recall. Probably one of our favorite kind of problems, I would bet. So what I like to graph it. So let's go ahead and graph. Here's an opportunity for us to graph 2 points in 3 space. Doesn't that sound fantastic? So let's do that. So we're going to draw our 3-dimensional space. I'm going to label it X, Y, Z. Again, we need to label it because there's more than one way to do this. So we need to label. So what I'm going to do is I'm going to use this little box method that we were looking at to plot point A, which is 8 to 13. So I'm going to say this is 8. That's my X coordinate of 8. We'll go with this being about 2. And then, we'll go with this being about 13. So now we're going to do our little box, right? Our little rectangular prism and kind of connect those together. Okay. And so we want, this to come up. We want this to be parallel, so we kind of go out like that. Okay. So my line is a little jagged. There we go, like that. Okay, so that's a fairly, it's not that great, but it's a fairly decent, this would be our point A. Okay, that's point A. So just for fun, let's do point B in a different color, just so we can see it a little bit better. So point B, we're going from, let's just go do it in red. So we're going from, we have a X value of 3, So let's just kind of say that's 3. We have a y value of 10, so we'll go out here for about 10. And then we have a z value of 4, so let's make that 4. So again, we want to make our little box, so we're going to make the x's and the y's meet. We're trying to stay parallel to this axis. And then we're going to come up to the 4, cross to the 4. Okay, making those. There's my side of my box. Let's make the other side. Okay. So my point B would be here. That would be point B. And now I'm going from A to B. So we're really looking like this, from A to B. That's what we would want our vector to look like, that we're going from A to B. Okay, so we want to go 70% of the way from A to B. So like we did in 2 dimensions, we're going to draw a vector from the origin to what we think is about 70%, right there. That would be O, and we're going to call that P. And then we're going to draw another vector to point A. So basically we have OP, so this is the vector we're interested in. OP is going to be equal to OA plus AP. AP would be this one right here. Okay, so we know that AP is 70% of the way to AB, to B, all the way. So we're going to say is we're going to replace OP is OA plus 70% of AB. So now we need to just put numbers in. So OP, that's what we're looking for, is going to be. So OA is just this vector from the origin to A, which is simply just 8 to 13. I mean, that's the vector from O to A. From the origin to A is simply that point, because that's a standard form vector. Plus 7/10 of, now let's go from A to B. We already wrote that vector. It's up here. -5, 8, -9. So that's the, the arithmetic that we need to solve. So I have 8 to 13 plus, so I'm going to distribute the 7/10 into this vector AB, and I get -7/2. 7/10 times 5 is -7/2. 7/10 times 8 is 56/10. And 7/10 times a -9 would be a -63/10. And now, yes, fun with fractions. You're wondering, oh my goodness, would I have a calculator for this? Perhaps if the numbers were this crazy, I would probably let you use a calculator. So we would add those two vectors together, and we get 9/2. And then we get 38/5. Those are great fractions, aren't they? And then we get 67/10. And that's the vector OP. Now they want the point. Well, the point would simply be 9/2, 38/5, and 67/10. That would be my point. All right. Okay, hopefully that was fine. All right, sounds good.